Have you ever noticed how the strength of an invisible interaction, like static cling or the pull of a magnet, seems to diminish remarkably quickly as objects move further apart? This intuitive observation holds true for one of the fundamental forces in nature, the electrostatic force. Understanding this relationship is absolutely critical in electrical engineering. The electrostatic force between two charged objects significantly decreases as the distance separating them increases. To be precise, the strength of this force is inversely proportional to the square of the distance between the centers of the charges. This means that even a small increase in separation can lead to a substantial reduction in the force experienced. This fundamental behavior is governed by Coulomb's law, named after French physicist Charles-Augustin de Coulomb. The law states that the magnitude of the electrostatic force between two-point charges is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance separating them. This inverse square relationship is key. Consider this. If you double the distance between two charges, the electrostatic force between them becomes 1/4 as strong. If you triple the distance, the force reduces to 1/9 of its original strength. This rapid decay occurs because the electric field lines, which representing the force, spread out over an increasingly larger area as you move away from the charge, effectively diluting their influence. For electrical engineers, this precise understanding of how distance impacts electrostatic force is invaluable. It directly influences design decisions in a multitude of applications. For instance, in designing printed circuit boards, engineers must carefully consider the spacing between conductive traces and components to manage parasitic capacitances and prevent unwanted electrical interference. In high-voltage systems, adequate insulation and separation distances are crucial for preventing electrical breakdown and ensuring safety. Even in microelectronics, controlling the precise distances between charged structures is paramount for device functionality and reliability. The inverse square law is not exclusive to electrostatics. It is a recurring theme in many areas of physics. You will find similar relationships governing the force of gravity between two masses and the intensity of light or sound as it propagates from its source. This universal nature highlights a deep mathematical consistency in how various physical quantities behave across space. Furthermore, understanding this relationship allows us to define and comprehend electric field strength, which also diminishes by the inverse square of the distance from a point charge. Grasping this inverse square relationship is a cornerstone of mastering electromagnetism and its applications. It moves beyond a simple theoretical concept, offering you a powerful predictive tool. This knowledge empowers you to intuitively understand and quantitatively analyze how charged particles interact across various distances, enabling you to anticipate and design for complex electrical phenomena with greater accuracy and insight.